Hello dear students, Assalamu alaikum. I hope you are doing fine. My name is Engineer Mir. I am lecturer in Department of Technology, Southern University of Science and Information Technology, Peshawar. As I am teaching you the subject Design of Hydraulic Structures, today is your lecture number 7. In lecture number 7, we will study about Lane's weighted creep theory. As we already started about seepage theories, we have already studied about Bligh's theory. Now we will study about Lane's weighted creep theory. Bligh, in his theory, had calculated the length of the creep by simply adding the horizontal creep length and the vertical creep length, hereby making no distinction between the two creeps. As we already studied the Bligh's theory, in which he had calculated the creep length by making no distinction between the two creeps, that is horizontal creep and vertical creeps. However, Lane, on the basis of his analysis carried out on about 200 dams all over the world, stipulated that the horizontal creep is less effective in reducing the uplift or in causing loss of head than the vertical creep. Whereas Lane, on his statistics and analysis, which he carried out on about 200 dams all over the world, he added that the horizontal creep is less effective in reducing the uplift or loss of head or in causing of loss of head than the vertical creep. He therefore suggested a weightage factor of 1/3 for the horizontal creep as against 1 for the vertical creep. So Lane, on his analysis, suggested that horizontal creep is less effective than vertical creep, and the horizontal creep is less effective about 1/3 times the vertical creep. Means that the horizontal creep is 3 times less effective than the vertical creep, or you can say that the vertical creep is more effective than the horizontal creep. L is equal to LH divided by 3 plus LV. He gives this equation for the creep length, in which he divides the horizontal creep by 3, which means that the horizontal creep is 3 times less effective than the vertical creep. Thus, in figure, the total Lane's creep length is given by L is equal to D1 plus D1 plus 1/3 L1 plus D2 plus D3 plus L 1/3 L2 plus D3 plus D3. Here, as Lane already stated that the horizontal creep is 3 times less effective than the vertical creep, so he divides the horizontal creep by 1/3. Here L1 and L2 are the vertical creep. As you can see in the figure, L1 is the distance through which the horizontal creeps occur, and also L2 is the distance through which the horizontal creeps occur, or seepage of water occurs. So, according to Lane's theory, or according to Lane's, the vertical creep is or the total creep is equal to D1 plus D1. Here this length is equal to D1 and this length is also equal to D1. The water starts creeping from A and moves along the bottom contour of the structure and moves here up to here. So this length is equal to D1 and also this length is equal to D1. So 2 times D1 or D1 plus D1. This length is the horizontal creep, and according to Lane's it is 3 times less effective, so divide this by 3 or plus 1/3 into L1. Next is this creep length, which is the vertical creep length. This length is equal to D1 and this length also equals to D1, so 2 times D1 or D2 2 times D2 or D2 plus D2. This length again is equal to L2, and it is the horizontal creep, which is 3 times less effective, so divide this length by 3 or 1 over 3 into L2 plus, again this one length is d3, this is also d3, these two heights equal to d3, so 2 times d3 or d3 plus d3. Now 1 over 3 into L1 plus L2 is the horizontal creep, plus 2 into d1 plus d2 plus d3 is the vertical creep. L1 plus L2 is equal to the total width of the structure, which is equal to B. So replace L1 plus L2 by B. So total creep length according to Lane's theory is equal to 1 over 3 into B plus 2 d1 plus d2 plus d3. This is the equation for the total creep length according to Lane's theory. Now, safety against piping or undermining. To ensure safety against piping or undermining according to this theory, the creep length LL, which is the Lane's creep length, must not be less than C1 HL, where HL is the head causing flow and C is the Lane creep coefficient given in the table. So the total creep must not be less than this equation, which is CHL, where HL is the head which is causing the flow and C is the total creep length, and C is the Lane's creep coefficient, which is given, whose values are given in the table below. For very fine sand and silt, the value of Lane's coefficient C1 is equal to 8.5 and the safe hydraulic gradient should not be less than 1 over 8.5. Similarly, for fine sand it is 7 and the safe hydraulic gradient should not be less than 1 over 7. For coarse sand it is 5 and the safe hydraulic gradient should not be less than 1 over 5. Gravel and sand, for gravel and sand it is 3.5 to 3 and the safe hydraulic gradient should not be less than 1 over 3.5 to 3, 1 over 3. For boulders, gravels and sand, the Lane's coefficient is equal to 2.5 to 3 and the safe hydraulic gradient should not be less than 1 over 2.5 to 1 over 3. Similarly, for clay soil, the Lane's coefficient is equal to 3 to 1.6 and the safe hydraulic gradient should not be less than 1 over 3 to 1 over 1.6. Note, the hydraulic gradient, that is HL over L, is then equal to 1 over C. Hence, it may be stated that the hydraulic gradient must be kept under safe limit in order to ensure safety against piping. As from this equation, which is L is equal to CHL, HL divided by L is equal to 1 over C1, and we have to ensure that the hydraulic gradient should be less than or equal to the 1 over C in order to safeguard our structure against the piping or undermine. Number 2, safety against uplift. Same formulas as in Bligh's theory. So for uplift pressure, the same formulas are used in Lane's theory as in Bligh's theory. Now, using Bligh's theory and Lane's weighted creep theory, uplift pressure at any point under the structure, it can be calculated using the following formula. The following formula is used to calculate the uplift pressure at any point under the structure by using Bligh's creep theory and Lane's weighted creep theory. The equation is, or the formula is, UA is equal to H into 1 minus LA over L, where UA is the residual uplift pressure at any point, for example A, and H is equal to total uplift pressure at the upstream side or the total head of water which causing the flow, and LA is the creep length up to point A. It should be any point, but in this case it is point A, and L is the total creep length of the structure. So according to this formula, we can easily calculate the uplift pressure at any point under the structure. Now we have example. In example, we have to find the hydraulic gradient and the head at point D of the following structure for static conditions. The water percolates at A and exits at B. Here is the figure in which we have to find the hydraulic gradient and also the head at point B. The water starts percolating at A and exits at B. We have a head of 6 meters which causing the seepage. The thickness of the floor at point A is 2 meters. Also the thickness of the floor at point B is 2 meters. The length of sheet pile at point A is 5 meters, while in intermediate it has 3 meter length, and the sheet pile at the B point or at the downstream side have a length of 7 meters. The distance between point A and point D is 15 meters, while the distance between the sheet pile at point A and the intermediate pile is 10 meters, while the length between the intermediate pile and the pile at the downstream side is 20 meters. Now, using the creep's theory, we will calculate the total creep length, which is equal to LC equal to 2 plus 5 into 2 plus 10 into 2 into 3 plus 2 into 2 into 7 plus 2 equal to 64. Here, the total creep length according to Bligh theory is equal to 2 plus 2 times 5. Here the water starts percolating. Water will seep through this 2 meter structure, this 2 meter depth, which is the thickness of the floor. Then water percolates up to this 5 meter. Then it will turn and then again it will start move through this length, which is 5 meters. So 2 plus 2 into 2 multiplied by 5 or 2 times 5. Then the water creeps along this length, which is 10 meter. Then again the water creeps along this 3 meter, which is 2 times 1 is this one. Once the water will move on this side and then the water will move on this side. So 10 plus 2 into 3. Again the water moves along this horizontal distance, which is 20 meters. So plus 20 plus again this length is 7 meter and this side is also 7 meters. So 2 times 7 meter, because the water will move along this side and also this side, and at the end we have to add plus 2, which is the thickness of the floor. So we will get the total creep length according to Bligh theory is equal to 64. Now we have to find the hydraulic gradient. Hydraulic gradient is equal to, which is hydraulic gradient is denoted by I equal to HL over L or delta H over LC, where delta H is the head causing the seepage and LC is the total creep length. So 6 divided by 64 will give you the hydraulic gradient, which is equal to 1 over 10.66. Now according to Bligh's table, the structure is safe on the gravel and sand, but not on coarse and fine sand. As remember, hydraulic gradient HL over L should be less than or equal to 1 over C. So by using this value and the Bligh's table, we have found that the structure is safe on gravel and sand, but not on coarse and fine sand. Next, we will find the creep length up to the point D, which is denoted by LCD, means creep length up to point D equals to 2 plus 5 times 2 plus 15 plus 2 times 3. Coming to the figure, here 2 is the thickness of the floor, so the water starts creeping from this point up to this. Here the length is 2 meters. Now again the water starts creeping up to this length, which is 5 meters. Then the water turns and creeps up to this length. Again this is 5, so 2 plus 2 times 5. Then this length is 10 meters. So, or you can easily calculate by first taking the vertical length, which is 3 meter plus 3 meter, or 2 times 3 meter, then this horizontal total distance, which is the 15 meter from A to D, and this will give you the total creep length up to point D from point A, and the creep length up to point D is equal to 33 meter. Now we have to find the residual uplift pressure head at D, which is equal to UD, means uplift pressure at point D is equal to delta H into 1 minus LCD divided by LC. Here delta H is equal to 6 meter and LCD already calculated 33 meter and LC is equal to 64. So putting the values, you will get the residual uplift pressure head at point D is equal to 2.9 meter. Now the thickness of floor at any point should be sufficient to resist the residual uplift pressure. If HD is the unbalanced head at point D, then HD is equal to UD minus elevation of point D minus elevation of the downstream flow, which is equal to 2.9 minus 0, means that is equal to 2.9 meter. Note, point D is at the same level of downstream floor level. So this means that the head at point D is equal to uplift pressure at point D minus elevation of point D minus elevation of the downstream floor. Since the point D is at the same point of or at the same level of the downstream floor, so this means that the elevation of point D minus elevation of downstream floor is equal to 0. So the head at point D, or the total head at point D, is equal to 2.9 meter. Now the thickness of the floor TD at point D should be HD divided by G minus 1, where G is the specific gravity of the concrete floor. Let's GS is equal to 2.24, then TD is equal to HD divided by G minus 1, which is equal to HD is equal to 2.9 divided by G is 2.24 minus 1 equal to 2.34. So this is the thickness of the floor which is required to be provided at point D. The thickness of the floor is calculated by this formula: TD is equal to HD divided by G minus 1, where HD is the head at point D and G is the specific gravity of the concrete floor, and let its value is 2.24 and HD is already calculated, which is 2.9. So by putting the values, you will get the thickness of the floor at point D, which is 2.34. So this much thickness should be provided to safeguard the structure against the failures of seepage. How to safeguard the structure against the uplift pressure, or so that the structure should be safe against the uplift pressure by balancing the uplift pressure through the weight of the structure. Now we have to by using the lanes weighted creep theory, we first calculate the length of the creep according to lanes creep theory, which is, so according to lanes theory, the total creep length is equal to 2 plus 2 times 5 plus 2 into 3 plus 2 into 7 plus 2 plus 10 divided plus 20 divided by 3. As we already studied that lanes say that the vertical creep or the horizontal creep is less effective than the vertical creep. So the horizontal creep is divided by 3, while the vertical creep is kept as same. So the total creep length according to lane theory is equal to 44 meter. Up to point D, the lane's weighted creep length is equal to 2 plus 2 into 5 plus 3 into 2 plus 15 divided by 3 equals to 23. Here also the horizontal creep is divided by 3 and the total creep length according to lane's weighted creep theory up to point D is equal to 23 meter. Now the hydraulic gradient according to lane weighted creep theory is equal to HL over L is equal to delta H over LWC, which is the lane's weighted creep length is equal to 6 divided by 44. So the hydraulic gradient is equal to 1 over 7.3, and according to Lane's table, the structure is safe on fine sand but not on very fine sand. Similarly, the residual uplift pressure head at point D UD is equal to delta H 1 minus LWCD divided by LWC is equal to 6 into 1 minus 23 divided by 44 equal to 2.86. So this is the total residual uplift head at point D. So now using the equation TD is equal to HD divided by T minus 1, you will get the total thickness of the floor at point D according to Lane's weighted creep theory. So putting the values by assuming G value is equal to 2.24, putting the HD value 2.86, you will get the thickness of the floor is equal to 2.3 meter. So this much thickness should be provided to the floor at point D to safeguard the structure against the uplift pressure, or the uplift pressure should be balanced by the weight of the concrete floor. And this is the end of our today's lecture.